In this video, let's talk about asynchronous programming in JavaScript by first understanding how JavaScript executes code and the role of the event loop, among other things. So let's begin. To understand what synchronous and asynchronous code means, it is important to step back a bit and dig into how JavaScript actually executes your code. The first thing to understand is that JavaScript is a single-threaded language. A thread is simply a mechanism for sequentially executing code. Languages like Java are multi-threaded, which means that they can take advantage of multiple processor cores to implement concurrency by spawning multiple threads that can handle tasks in parallel. And this enables you to execute tasks simultaneously. JavaScript, on the other hand, is inherently a single-threaded language, which means it runs in the browser on a single main thread, along with other things like rendering or painting the page, which is how you see visual updates, handling user events like mouse clicks, keyboard, etc., and of course, your JavaScript code. This can slow things down if your code is inefficient, and it blocks the thread of execution because it's not just your code, but you're also blocking the only mechanism that the browser uses for rendering the page and offering interactivity, among other things. Modern JavaScript offers ways to improve this situation and circumvent issues with single-threaded processing, and we'll talk about it later in this module. Now, inside your JavaScript engine, such as V8 in the case of Chrome, there is a data structure known as a call stack. Think of it as a to-do list which the JavaScript engine needs to execute your code. Only that items that go in first cannot be processed if there are other items pending processing on top. For instance, in this case, when you start to execute code, the add_nums function is executed first and it goes up on the call stack. This is known as a frame. The numbers are added, console.log is added to the stack, executed, and the function exits. Then the subtract_nums function goes up on the stack, followed by console.log, which prints out the result, and the call stack clears out. All of this looks fine. But now let's introduce a hypothetical function called processData. We are running this function in between calls to the add_nums and the subtract_nums functions, and let's imagine that processData has to do some very heavy number crunching and will take time to finish. When we run this code, add_nums is executed and we get the result. Then our processData function goes up on the stack, and since it takes time, it just sits there on the stack until it finishes execution. This means that until processData exits, the subtract_nums function cannot go up on the stack for execution. Effectively, our single thread is blocked. So processData here is blocking the execution of subtract_nums, and this can be a problem if you have several such functions that can choke up your thread. It is also important to note that your browser uses the same thread to update the UI and offer interactivity. So a long-running blocking function will block and hang up your web page for the user. If you see the way the execution is taking place here, it is a sequential list of tasks. This is called synchronous execution, where a task has to wait for the preceding task to finish before it gets a chance to execute. So, for instance, loops in JavaScript are synchronous and can block your code quite literally. Let's see another example. Observe the code for a bit. Function 3 here is calling function 1, which in turn calls function 2. Here, the execution begins at function 3, which goes on the stack. Then, function 1 is called and placed on the stack. Function 1 calls function 2, which goes on top of the stack. So in order of execution, function 2 finishes its job and returns the value. Then function 1 gets its act together with the value from function 2, and once it finishes, function 3 continues processing and does its job before the call stack clears out. To understand potential problems with this sequential system of execution, which we know as synchronous execution, imagine you press a button to perform some task and the web page blocks completely until the task finishes. That cannot be good. To solve such problems, browsers implemented mechanisms such as the set timeout and set interval timer functions, which we saw earlier in this course. These are part of a set of APIs known as web APIs, which are not part of the JavaScript engine but are provided by browser implementations. Now, let's see what happens when we bring set timeout into the picture. Here we have three functions that are being called one after the other. Don't worry about the several other things that you see on this slide. I'll explain these in just a moment. Just follow along. So, the first function is put up on the stack, is executed normally, and exits the stack. Then the second one is brought up on the stack, and this time we have set timeout in the picture, which is supposed to count up to 10 seconds or 10,000 milliseconds. At this time, this function almost instantly exits the stack and is transferred to the web APIs where the timer starts running. And since the call stack is now free, the third function goes up and does its job, and the call stack is free again. Now, after 10 seconds or so, the web APIs are done with the set timeout, so they take the included callback function, which you express as the first argument to set timeout, and places it in a task queue, which is once again like a list of items where the oldest item is executed first. Note that this is different from the way the call stack works. And this is where another important construct, the event loop, gets into the picture. The event loop is literally like a loop which runs as soon as there is something added to the task queue. But it runs only when the call stack is free. So keep this in mind. The event loop will run only when the call stack is free. So the moment the call stack is free, the event loop scours through the queue and starting from the oldest entry, processes everything. Here our callback from the set timeout is in the queue. The event loop plucks it out, throws it up on the call stack for execution, and it's executed, and finally the stack clears out and you get the result. This way, you were able to run code in a non-blocking way. The second function did not come in the way of the first and the third function. This is what asynchronous programming is all about. It is the process of performing multiple concurrent and non-blocking tasks. Concurrency is a big thing and is extremely useful in situations where you must perform a long-running task such as sending or fetching data from a server or an API. In fact, without knowing it, you have been playing with asynchronous code all this while. One of the best examples of async code are event listeners, which once again are provided by the DOM and are not part of the core JavaScript language. Once registered, the event listeners continue to monitor for events, and whenever that occurs, they push the event handler callback into the queue from where the event loop picks up, drops it on the stack for execution. But the key thing, event listeners never block your code and continue to run in the background. Likewise, there are other things that work in an asynchronous fashion, such as remote communication mechanisms. We'll get to play with these in the next module. So now, how do you handle asynchronous execution? Well, constructs that provide asynchronous abilities in the browser have traditionally provided a callback-oriented interface, which you can see here. You've been using it all this while with event listeners. But do keep in mind, not all callbacks are asynchronous. For instance, the callback here isn't asynchronous and the loop runs in a sync fashion for all elements in the array. Now, modern JavaScript also offers a handful of features which enable you to write better async code. For instance, instead of using callbacks, we can use promises to handle async code elegantly. And as an extension to promises, async functions enable us to implement synchronous code-like abilities with asynchronous code. This, as you'll discover, is quite interesting. We also have generators, which are special type of functions that can be paused and stepped through as needed. Lastly, we have web workers, which are a true game changer because they allow you to offload heavy tasks off the main thread to worker threads, which can do the heavy lifting in the background and send back the results once done. There are numerous benefits to using asynchronous programming.
But like all things in programming, it's not something that you should use in every instance. Want to learn more about when and when not to use it? We've got your back and we'll help you learn hands-on. With our outcome-based immersive learning approach, we are fundamentally disrupting the way new age technologies are learned. You'll get to learn, practice, assess, gain insights on your learning, and personalize your learning journey on our easy-to-navigate AI-powered skill-building platform, Prism. Stay tuned for more such videos and explore more about how you can equip yourself with immediately demonstratable in-demand skills that'll help you get job ready. And don't forget to subscribe and press the bell icon to get notified so you don't miss out on our upcoming videos.